if I do like this and like this, all right, so again, we are, to make sure that everybody is on the same page, we looked last week, at the Langevin equation. We said that this is x dot dot plus gamma x dot. So there can be a force plus a force, but we didn't look at this with the force. And then we said that there was a coefficient which is 2 epsilon gamma square root w dot, where w is Brownian motion. Thanks. W is Brownian motion, continuous time Brownian motion. Epsilon and gamma are constant. This is usually in physics, this is called the energy. This is in kT, for example. And this is gamma, this was the viscosity. Okay. And so last week, we said, we looked at the case where F was equal to 0. And we derive this equation from consideration, saying that you have a single particle. We have a particle, x of t, that moves in a medium where the ball is getting reflection. And this is why, this is due to this reflection, that you get here the Brownian noise. And this is due to an assumption that the drag force is linear. Otherwise, you see, you know that in airplanes, when they go fast enough in some hydrodynamics at very high speed, it's not anymore linear, because this is an assumption. This is a phenomenological. You know, it can be gamma. This can be to a certain power of the velocity. This is how people have modeled supersonic things in fluid. But this is not our goal here. This is to see where answers assumptions, or the physical assumptions, the modeling, versus derivation. Okay, so this is where we got last week. So wait, where did we say? Yeah. So and then we didn't say what happened for gamma large, right? So for example, have we said that for gamma large, let's say when gamma goes to infinity, large enough, compared to you know, any relevant scale, when gamma goes to infinity, this equation converges in the sense that the probability density function converges to what is called the Smoluchowski limit of the Langevin equation. That is, when gamma is infinity, it goes to infinity, is large, then this equation converges in terms of the probability density converges, except for extremely short time, to gamma x dot plus f equal 2 epsilon gamma w dot d. We haven't said this, right? That when gamma goes to infinity, let's say equation, let's say 1 gamma, equation 1 gamma converges. This means of convergence. So this is in probability convergence to this stochastic equation. We haven't seen that yet. Okay, so I'll show you how it goes, why you have this, and what is the limit of this. Because you can find the limit of this for short time. For short time scale, and this is important when people are describing chemical reactions. Chemical reactions for very short time of binding, you have the limit of the Smoluchowski equation, because this is not correct, this approximation. We will see where it comes from. It comes when we have the expression of the probability density function of the diffusion. You will see it's clear where it comes from, but now I'll mention it. So this converges for t in the interval t bigger than a capital T, let's say, t0. And this t has to do with basically is 1 over the friction coefficient. This should be 1 over time, no? Yeah. So this is the time. Below, after the, you can do this after this time. Below this time, no, it's incorrect. You have to go back to the full equation. Okay. All right, so let's discuss this. So why am I switching? Or maybe, okay. So maybe there are a few remarks. Few remarks before we go into this. So this is what I just said at the beginning. So previously, an assumption, one assumption of the derivation is the linearity of the friction force. That is, F was minus gamma velocity. So this is a linear approximation, linear approximation. Now, instead of this, you can have what we call a time kernel, a kernel that accounts for the history. And so, for example, this is the diffusion in a crystal, for example. Diffusion in a crystal is actually modeled with a different properties that I will write now, the Langevin equation, which is the acceleration plus the integral from 0 to t of phi of s, and then you have to integrate over all the path of the velocity ds, and there can be possibly a potential, and psi of t if the fluctuation is the noise term. And this satisfies the correlation, which is the expectation of any 2 time ti tj for any 2 times. So psi is the noise, is gamma. Gamma is the viscosity, that the energy cavity phi of any of these 2 time ti minus tj. So for any 2 time ti tj. And so I'm getting hot. And so in a crystal, phi of s, this has been found empirically, phi of t is sine omega t divided by omega t. Okay, so what are we discussing here? We said that a different model, so what is a crystal? You know, a crystal is a periodic organization of atoms with a certain structure. And now you're interested of the Brownian motion of a particle inside this structure. How do you describe this? It turned out, after years of work, that the description is not something where you just look at the velocity at one point. You have to take the path from 0 to the point t with a certain kernel. But if you do that, and if you want to respect fluctuation dissipation, you need to have this relationship, which I'm not going to prove here. It's going to be, it will take me another 2 hours. That there is the connection, that the same that you have here, square root of gamma and gamma. This is the connection that you need to respect. This is, again, I'm not describing this. I'm just showing to you that there's a different type of models that can be used for different application. For example, Yeah, it is. It is. Because you respect, you have here the your trajectory x of t. I mean, if you're in dimension 2 and dimension f, you have your all steps, your all variables, and it satisfies a stochastic equation. Now, what you can have from this is, for example, you know what is the colored noise? The colored noise is a noise passed through a low-pass filter. A colored noise, instead of, so how you build a colored noise, basically, you have a noise which is minus alpha u plus, let's say, beta w dot. This is Brownian motion. This is a w dot that is here. And here you are killing the high frequency. Right? You know what is a low-pass filter? Oh, okay, so just, you know, you don't care about the name of this. This is the solution, so U is called a colored noise when it is solution of this equation. You generate, how you generate such a noise? You just use this stochastic equation. And again, this is, so you can now imagine a particle moving with this type of noise. So there are different possibilities for the noise, and different possibilities for the linear term here, which would represent here the history, because you integrate from 0 to time t. Okay, so this is, those are simply, yeah, and so I have to tell you, because there is a huge literature on this, what is called anomalous diffusion. You will find a lot in the literature. Anomalous diffusion is the case where phi of t, well, it's not very well written, but anyhow, phi of, well, okay, phi of t is t minus s or s minus t to power alpha. It should depend really on t and s, right? So this is true only for s between 0 and t. So that you take this and you put it in here. All right? And when you look in the literature about the anomalous diffusion, this corresponds to solving this equation using this type of memory with this particular kernel. This is called a kernel. And there's an industry of trying to understand what are the properties of the trajectories that satisfy this condition, that have this type of memory kernel. Okay? All right, so this is the remarks. So now I'm closing the remarks. So this was the remarks. And now we are going to this friction approximation. So Smolachowski approximation. So for understand this, let me remind you that we had V dot plus gamma V equals F, right? Yeah. And then we had X dot, which was the velocity. So in the class last week, yes?
For the anomalous diffusion, if you look at the correlation of the psi Ta and psi Tj, and if you take the phi you wrote below,
yes,
you mean that the second moment would diverge?
Sometimes, yeah, there is no second moment. It depends on your process.
What does it mean physically that the second moment diverge?
I don't know. I mean, physically, what do you mean physically in terms of, for example, in classical diffusion, when you look at mean first passage time outside the domain, there is no mean first passage time because this moment diverges. Okay, suppose you are interested in how long it takes for a particle to enter here in this domain. So the time it takes is the time when you average over all the trajectories like this, which can go to infinity. So this is an example where the first moment, the second moment of the time, that goes to infinity. So now what is the meaning of this? It's very hard to, you need to have a specific physical settings to understand what's the consequence for the physics. I mean, mathematically it diverges. Now you're asking what's the consequence? It depends on the question you are asking. For example, here, if you do mean first passage time even for Brownian motion, if you're outside the domain, the time and the square of the time is infinite. All the moments are infinite because of the situation you are looking at. If you do this inside, they're all finite. So there is no absolute answer to your question. I'm saying it depends on the situation that you want to characterize. I think this is what I can say. But there is an entire literature. I mean, people have looked at properties like mean square displacement to some power, or look at how it behaves for delta t small. So then, you know, you have some formal calculation. For example, it's very hard to do something with the give a solution to the that's what we are going to see, the Fokker-Planck equation, which is the probability to find the particle for an anomalous diffusion, or what is, for example, the mean first passage time. Everything is through the mathematics that you can answer some of the question you're interested in. Okay, so now let's go back to this. I wanted to integrate this equation twice. So you agree that x of t, if you integrate v, so what we have seen last time we saw that v of s is v0 exponential minus gamma s plus the integral from 0 to s of exponential gamma u minus s f of u du, correct? And now I want to integrate this one more time to get x. So for this, you just, you know, formally integrate this. So this is x0 plus v0, and if we integrate, this will be 1 minus gamma, so this is now t divided by gamma, right? Plus the integral from 0 to t of the integral from 0 to s of exponential minus gamma u minus s f of u du ds. You agree? I just, you know, integrate everything. I did nothing else. And now if you change the order of integration, instead of integrating first u and then s, you just reverse, and you get here the kernel that appears. So you'll do it at home. This is integral from 0 to t of 1 minus gamma of u minus t divided by gamma fu du. And now if I put everything here on the left side, I get x of t minus x0 minus v0 1 minus exponential gamma t divided by gamma equals, right? I just put everything here in the left hand side, and the only thing I haven't documented exactly is how you reverse here the integral, but this is not hard. You're right, you are integrating over a triangle like this, and then you do it like this. All right? So this is what you get. And now, so f of u, we said last time, this is the Brownian motion. And now we integrate a deterministic function over Brownian motion. So what is this? This is, so this, which is equal to this, which means that this is Brownian motion, and then we just have to change the time or get the variance. I mean, how you characterize this quantity? What is the mean of this? If you average, this is 0 because f of u is correspond to a Brownian motion. And now the only way to characterize it, I mean, fully, is to calculate the second moment, which means that this entire thing here is a Brownian variable with a moment, a second moment that we have to calculate. Now, how do we do this? So, okay, let's just write down what you guys said. So, if you call this is now our kernel, g of u, let's say minus t. So, this j of u minus t, f of u, the expectation, integration from 0 to t, the expectation of all of this by definition, because this is a Brownian motion and this is deterministic. So this is the integral. Okay, let me write it once. This is j of u minus t, expectation of f of u, which is Brownian motion, which is 0. Okay, and now we are left with the second moment. So, you know, we already did it, so I'll go. So this is the expectation of the integral of 0 to t of g of u f of u du squared. So how do you calculate this? We did it several times. Either you decompose in a sum, or you want me to do it one more time, just to practice? Yeah? Okay. All right. So this is j. For example, you can you can look at this as an approximation by the sum of g k delta t f of k delta t multiplied by delta t multiplied by j of q delta t. You know, something squared, this is squared, this is twice the same. So I'll sum over k and over q. This is something, you know, that goes square. So this is j q delta t f q delta t multiplied by delta t, and we have to get some, and that's it. And we have to take the expectation of all of this. So everything will be 0 except when k equals to q. And so we are going to be left with the classical thing, which is g squared k delta t. And those are the Brownian increments. So we are getting then the this is d omega k. This is the expectation of d omega k squared, right? Because when k is different of q, this is 0. So we are left with something with only k. And by definition, this is exactly delta t. And so basically, we are back to the integral because, again, I'm not going to detail this. You cut and then you go to the limit where the delta t goes to 0. So this is a Riemann sum. When delta t goes to 0, it converges to now the classical integral, which is gq of s ds. All right, and now what is the result? So this is this function squared, right? And where did I? Okay, I see. And also I forgot something. No. Yes. F. What was in the note? The expectation of f squared from last week. Expectation of delta q, delta k squared. You have it? This was 2q or 2 alpha or 2 gamma, no? You don't have the notes of last week? 2D. 2D? or 2q, I forgot how it was, how I wrote it.
2q delta t.
2q delta t, okay. 2q delta t, so here, this is not delta t, but there is a 2q multiplied by 2q, all right. So now this is 2q, yeah, okay. Is it correct? Is it correct, okay. Okay, so now what is this? You have to integrate twice, you have to integrate 1 minus exponential minus gamma t. So this is squared minus 2 exponential minus gamma t divided by gamma squared. And we have to integrate this from 0 to t, whatever, no, sorry, from 0 to s. Yes, from 0 to s. And this is ds. This is 2q divided by gamma squared. So what do we get? Just integrating 1 from 0 to t, it gives you t. Minus, so there is a 2. I'll start with this one. Is correct? Okay. Minus 2 exponential gamma of u minus t. Why do I get this here? Yeah, maybe. Yeah, so this was. Yeah, this is u minus t, right? So this is u minus t, so I have to integrate with respect to u, and I have a t. So this should be exponential of minus gamma of u of s minus t. And this is of s minus t. All right. So t is fixed, and you integrate with respect to s. Somebody is checking, right? My calculation. You don't rely on me. So this should be minus 2 exponential minus gamma t, exponential gamma t minus 1. You should redo them. Plus exponential minus 2 gamma t, exponential 2 gamma t minus 1 divided by gamma squared. Is it what you get? All right, so what did I do? You just calculate this quantity. Yeah, you just calculate. So this is, you have to calculate this squared. Yeah, this is what we're calculating now. So j of s, this is j of u of minus t. So this is, you replace u by s, you put it squared, you integrate. So it should not be hard.
There should be a plus in the middle.
A plus?
1 plus.
That's right. Minus, this is this one. Okay. Gamma t, then minus gamma s. I'm not sure this is correct, but I hope this.
Last one is 2 gamma and not gamma square. Yeah.
Here?
Yeah, 2 gamma, I would say.
Good. Yes, correct. Okay, now this is quite interesting because this is the variance of this quantity. So now we are ready to write what is the probability of our process x of t minus x0 minus v0. I mean, you could, well, okay, I write it this way, minus gamma t divided by gamma. Condition that, yeah, okay, this is clear that there is no conditioning because for t equals 0, x of t equals 0, and the derivative is v0, right, from this. So what is this? This is now a Gaussian of variance sigma t. So let's suppose we're in dimension 1 or 2 or 3. It's an important, so I'll put, let's say, dimension, okay, I'll do dimension 1. So it's 1/2 exponential of minus. So this is now a Gaussian. So this is x squared. So the probability that this equals, so this is x0 probability that this equal x, let's say, we have a Gaussian, so this is x squared divided by sigma 2 sigma t. And sigma depends on gamma. You agree? The sigma we have calculated, which is this, depends on gamma. All right. So now what happened? Yeah, this is I wrote it in dimension 1. If it's dimension 3, you have here, actually we can write, yeah, I'll do dimension 1 because it can be different in all dimension. I don't want to start introducing a tensor for the noise, that you can have noise. So let me do it just dimension 1. It's not very hard. If you have 3 independent equations in 3 direction x, y, and z, then we have 3/2. And if the matrix of the noise is identity, then you just have put a 3 here, and that's it. Okay. So now let's start the thinking. Up to now, this is the boring calculation. What is the meaning now of gamma large? We can look at how these behave when gamma is large, right? So we should look at this when gamma is large. So what do you get when gamma is large? Well, I hope these formula are correct. I think they are. So it's 1 minus exponential gamma t divided by gamma. You agree? So t is t. It doesn't move. Q is q. So I think q we had a value. Yeah, what is the value of q? Q. So sigma t. So this is 2q. So I wrote gamma. So q is actually gamma kt divided by m, something like this, right? Okay. So q depends on gamma. So we get 2 divided by gamma. And here there is a constant. Let's write it kt divided by m, which is unimportant, but we'll write it anyway. Multiplied by t minus 2 divided by gamma, 1 minus exponential minus gamma t. And now you said it was plus exponential, no, 1 minus exponential minus 2 gamma t divided by 2 gamma. So in principle, if gamma is large, this for t not 0, this is going to 0, right? This is the same. This is going to 0. This can drop. So in the first approximation, when gamma is large, this is like 2 kt divided by gamma m divided by t. So this is exactly 2d delta t, which is the classical diffusion tensor for the Brownian motion. So when t is large, so what happens if t is 0? If t is 0, for example, if you expand for small t, this is minus gamma t, so this is 1, 1 minus 1, there is a gamma, gamma and gamma goes. Then you don't have any more such a beautiful result. You see that if t is small enough, this approximation fails, which means that the convergence in probability, so now when gamma is large, this behaves like the same that is in here, except that gamma, sigma behave like this, which is exactly the diffusion, the probability distribution function for a pure diffusion process. You are with me? Which means that in the sense, these equations, this is called the Smoluchowski, 1914 or 1916. This is the Smoluchowski limit, that the Langevin equation, in a sense, converges to the Smoluchowski limit of the equation that has its name. Except, so this is for t, basically big enough. Gamma t should be something larger than 1 over gamma. Otherwise, it is not correct. And this is what is usually forgotten in many applications. Because this is something to remember when you do chemical reaction. And if you use the classical framework, that is x dot equals your potential well. Suppose you have a potential well, you have a particle, and you have a parabolic potential well. This is the plane. It comes here and enters into this domain. So this is modeled as x dot minus this interaction potential plus 2d square root of 2d w dot divided by gamma. So I divided, so I take the Smolokhovsky limit, which is written somewhere. Yeah, it's here. You divide everything by gamma. So you get force divided by gamma. This is the approximation. Now, of course, the question is that when the particle escape, what is the meaning of escape? Escape is when you are in here. You're at the boundary. So what is the next move to be done? Either the particle goes away, or it can go back. And in the simulation, you do this, but it can come back inside and outside an infinite number of times. It goes back and come back. It goes back, you wait some time. So this is completely artificial. This is artificial. This is due to the fact that here the approximation is not anymore correct. So when you go outside from the well, if you have for a certain time a ballistic propulsion, because this is the ballistic, you have a velocity v0, then you move away and then you don't necessarily come back. All right, so that's why I think it's important to think about it for any type of simulation and to see what is the limit of the model you are using. And it is important because we need to model this type of process. Okay, so this is called the Smolokhovsky limit. This is called the Smolokhovsky limit. And so we have shown that the probability density function, P, let's call it gamma, converges to P of a pure diffusion process as gamma goes to infinity. And for T, let's say, larger than a certain constant. This is pure diffusion. So this is, convergence in terms of function. So you can have any good space, L2, maybe more than L2 here. If you have outside this constant, we can have very strong convergence. Okay, so this is the what I wanted to say about this limit. Now let me give you, starting following this kind of ideas, let me give you some problem, something to think about, and examples. Examples and applications. So this I'm going to state, I'm not going to prove anything. Suppose you have a particle in dimension 1 that follows this equation, the full Langevin equation. So this is, for example, used, this type of equations, they are used to describe ions inside a channel. So let's start with the Langevin equation. For a particle located at position described by the trajectory x of t. So suppose, for example, you have a membrane of a cell. And then you have what is called the pore of a channel. So you have here, you can have a complicated potential well. So this is as a function of the space, let's say z or x. This is the profile of your potential well. I'll put it in blue. induced by the molecules. You know, you can have some residue that have all kind of shapes, and you are interested in the question. So this has been worked out for the last 20 years. How ions are going to flow through this structure. For example, what is the flux of ions through a channel, depending on the profile. So for this, you have to solve this equation, and you have to add here potential. For example, we have to add here plus V prime of x equals 2 gamma W dot. And this potential is the potential that you have here. So you can look at different questions. So one question that came out of this in a very simplified case is called the albedo problem. So the question is how to calculate the flux, how to compute the flux through a channel. So if you have V, for example, equal to 0, and you have something, an interval 0L, suppose you start with a velocity V0. You push a particle with V0. So the question that people have asked, and I'm not going to solve because this is actually mathematically, technically difficult, is what's the probability that the particle we start with a certain velocity will hit L before it goes back. All right, so this is for zero potential. This is called the albedo problem. So what is the probability? Find or compute the probability that the time to go to the left is shorter than the time to go to the right. Condition that at time 0 you start at position x equals 0 and with a velocity that goes inside, positive velocity. Where tau L, this is the first time that the particle hit, let's say, the left. What is left? Left is here. So the first time positive, or let's say define, let's say right, the first time that x of t equals L. And t left is the first time that x of t equals 0. Strictly positive. So, and you go with a velocity, that's why here this is strictly positive velocity, so that, you know, if you come back, because you make a loop, you just don't come back immediately. So this is actually a very hard problem to solve. It involves understanding, solving the Fokker-Planck equation in dimension 2, in the variable v, the velocity in the phase space, v, and x. And to look at the correct boundary condition. So if you want to do something analytically, here, this is not trivial. It has been looked at and published, there are some results published in the 80s, 86, 89, so 1986, 1989, in Siam Journal of Applied Math. Just to show you that those simple questions can have difficult answers, but so that it's important to have this in mind. So 1996, 1999, and this is from one of the authors, David Livermore. So if you do just Google search, or you can, you know, have these two papers. So what people are doing with this, they try to do simulation. They try to do correct simulations. So for example, what happened when you look at two charges, not one but two? Suppose you have the same configuration, you put two charges in the system. You put two charges. How do you calculate, for example, and they cannot, of course, pass each other. For example, there are two ions of the same charge, plus and plus, or minus and minus. They enter in here. So if this one is moving, then this one has to be pushed, because it will be pushed due to the electrostatic repulsion, plus the potential. So how do you study correlated particles? So the idea is what? Just to use two equations. So again, this is, I'll give, two more examples, and then we will move on to the Ito calculus. So again, I said that I'll do the Ito calculus, I'll do the classic that I used to do in Paris for many years, and then we will move on to the new type of calculation I want to show you with what we said at the beginning with the plan we had. So for what is the flux, I mean, how you state the problem? I'm not solving anything yet, just showing to you what the problem is. So if you have two correlated particles in the channels, two correlated particle ions in a channel. So how do we write this? We need two equations. So this is particle x1, particle x2, and we want that x1 never penetrates x2. So x1 minus x2, for example, they can always, we can have this condition that they cannot come too close, which means x1 and x2, they cannot be more than a. And so now we have two Langevin equation, x1 squared plus gamma, so acceleration velocity, plus we have a potential, so we have the potential of the well, this is the channel, plus the interaction term, x1, x2, equals noise, 2 epsilon gamma w1 dot. We have x2 dot, which is plus gamma x2 plus v prime channel on particle 2, plus the force due to, this is a force due to 2 to 1, and this is the force due to 1 on 2 of x1, x2. And for example, equal noise, 2 epsilon gamma, so we don't have necessarily the same noise. So this is W1 and W2. What is, for example, this V12 or V11 or V21? If it's completely symmetric, then V12 on 1 on 2 or V21, this you can take, for example, what is called the Lennard-Jones force. Lennard-Jones force, which is 1 over R6 minus 1 over R12. So it's a constant, C1 x1 minus x2 power 6 minus a constant. So the constants are known in the literature, x1 minus x6, x2 to the power 12. Okay, so this leads to a correlation. This is very hard, because actually the real space for this is what? If we have understood that here, you see, this is the space of velocity that I've drawn here, velocity, and this is position. So x and x dot. So this is 2 dimensions for one particle. If you want to analyze this, in dimension 4, if you want to see the configuration of the particle. For example, in x1, x2, if you impose a condition like this in your simulation, so this is x1, and this is x2. And this is x1 equals x2 when they are at on the diagonal. And now, if they want to be outside this region, so we have to have a band of radius a here, of size a, such that the particle cannot they cannot penetrate this band in this abstract space, otherwise they are too close. And so particle enter at position at. So what is the meaning of escaping? For example, if this is position L, if this is position L. Yeah, it's not great. Sorry, it's position L and L. You're in the square. So particle x1 should escape here, but if particle x1 is there, particle x2 cannot escape, so it has to go away. So there is, all the time, this creates some correlation. So this is x1, x2, and then on this you have to put the potential of the channel, that is the one generated in blue. Okay, so this is an example of writing a stochastic equation for a coupled system. So we've been seeing what happened for something with no correlation, but a potential well. Correlation, where you have to include this, plus the channel, plus noise. What do you do with this? If it's just equation to contemplate, you say, right, what's the point of doing all of this? Well, I understand this argument. This is what you do, for example, on a simulation. This is the equation that you put on the channel and you simulate like this. And you can get your statistics. Run 100 trajectory, look at the fraction that arrive to here compared to those who are living, what happened when you add an ion in correlation, and this will allow you to understand your system. This is what people did for 20 years. Understanding this by simulation, by finding the right equation. So, for example, at the beginning, they started with this and they found that everything went wrong. They didn't put the term here for the acceleration. Although, you could say that in a channel, maybe the Smolokhovsky limit is okay, but it's not, because you're in a very small domain and you are looking at very small time. The time to go through a channel is microseconds. And this is comparable to the time 1 over gamma, which is the time for friction, relaxation in a medium. Okay, so and then I'll give you sorry, I'm lost in the notes. Yeah, and now I'm going to give you, so if you're interested in all of this, the classical book about ionic channels, this is written by good biophysicist. This is the book of Bertil Hille, and this is like, the name is Ionic Channels and something. And the latest version is 2001. So you'll have some description of this plus the latest about trying. So it's still going on. So what are the big questions in this field? How do you select? Okay, when you make your pasta, what do you select when you shake your plate with the hole? What do you select? You select the big stuff, and the small go through. So you select the big ones, right? But now how do you do the opposite? How do you select the small and you let the go through? It's not answered. We don't know. And this is what happened. Some ionic channels. Okay, why people are studying ionic channels? Have you ever heard about ionic channels? Ionic channels are the basis of cell communication between internal and external. This is how they regulate their concentration of ions, of water. We have this aquaporin that regulate the concentration when we have water, salt, and sugar. So it remains an important question. So how do you select, for example, potassium versus sodium? They have the same charge. Some channels can select one, some channels can select the other. The difference is the size. So when can you select the small one? I mean, when can you select the big one and not the small one? One should go, but no, it doesn't go like this. So this is important. This is not solved, and nobody has a clear idea of how understand like in a generic manner this question. This is how people do it by simple elementary stochastic simulations of ions trying to move in a channel, where they try to understand how the pore of the channel, how this pore here of the molecules shape the potential, and you can have also this interaction between. I mean, it can be more complicated, but I don't want to go into more detail. Okay, and the last example I would like to show you is how do you amplify with Brownian motion? So this is now a question in transduction, cellular transduction. So the final application, so this is application number 3. So this was application number 2. Application 2. And this is application 1. So this is important. Now what I'm going to describe here for the process of phototransduction. So you know, I told you, I mean, I'm not sure, did I say that at the first class? That we can see a single photon. So if we can see a single photon, it means that you have one molecule activated and you have a cellular response. How come? Did I mention this? How this is done? It's not simple. It took 50 years and it's still not fully understood. But there is one step, which is the following. You have a photoreceptor, you look at it, you cut the photoreceptor in 2 parts, and there are discs. And now you look at a disc, and this is a disc that I have projected like this. If a light activates a rhodopsin molecule, it becomes activated. So you have, this is time. This molecule starts to be activated here. It is activated for a random time, Poissonian time. This is not Poisson. And then it is shut down. So this is a time, tau, and you can have a mean time, you know. For the time the molecule is activated, it is performing a Brownian motion. So you have such a Brownian motion. And now, here is the question. There are molecules, let's suppose they are fixed. They can also move by diffusion, and so yeah, and this is a, let's say, so you have a Brownian motion with coefficient of diffusion d, which is fixed. And then the molecule is only activated for this time. That is, afterwards, if it does any Brownian motion, nothing happens. It's only during this random time. And now there are molecules. And each time on the way it meets the molecule, with a certain probability, the molecule can be activated. So here is the question for you. After an average such a time, how many molecules are going to be activated? So each time, let's say, this Brownian motion hit this particle, it becomes activated with a certain probability, which we call, let's say, probability of activation. This is known, suppose. So I'm interested in what is the mean number. What is the mean number of activated molecules? Of activated. So we have a population activated molecule. Let's say the population is represented by its density. So you have a population of molecule, let's call it T. And there is a density rho of T. You know the density. Suppose this is known. So how do you do this calculation? Okay, so this is more or less the same. We need the same type of model. We need to have a Brownian motion. And now what we need is, of course, molecule, they have a size, right? So how do we account for the size? We can say that instead of looking at just a trajectory, we can look at a bend near this, so we get something like this, right? I mean, I'll do it. So, you know what is the name of this? And so on. You can see this drawing. So this is called the Wiener sausage. It has been introduced by Wiener maybe 70 or whatever years ago. And now this is, so we have a band, which now makes sense. So we have something with a certain size, let's call the size epsilon, which can reflect, for example, the size of the active part of the protein that is moving. And during a certain time tau, we would like to see what is the surface that is covered. Then the surface covered multiplied by the density of particle will give us some information about the number of particles of the type T that is inside. Right? And then for each one that is inside, there's a certain probability of activation, then we can calculate this. All right? So this is the... You want me to... Let's maybe look at it together, and then I'll finish this example. This will close our example type. So you know how to treat, how to describe the Wiener sausage. So let's call the Wiener sausage what I just described to you, which is this ensemble. This is the ensemble made by all the balls centered at the Brownian motion x of s of radius epsilon when s went from 0 to, let's say, the time that it is activated, capital tau. And you take the measure, the surface associated to this. So this is the Wiener sausage, this is ensemble. And I'm taking the measure, the integrals of the indicating function of this, which give you the surface of this, you know, in whatever unit, meter square, micrometer square, this gives you this quantity. But what is interesting, and this I'm not going to prove it, that in dimension 2, this behaves like pi tau divided by log of 1 over epsilon. Epsilon is the size, pi is pi, and tau is the time. And this is a formula due to Mark Katz from the Feynman-Katz integrals, 1974, Rocky Mountain Journals. For those of you who will look at it after the class. Rocky Mountain Journal. So, and this is for tau small. This is an asymptotic formula. What is nice, of course, is there is a phase of formulation and there is a phase of computation, how you do asymptotic analysis, which I'm not doing here, we will do later on in the class. How you calculate, but for this part of the class is to understand what are the questions, how you formulate them, and what are the tools to address them. Okay, so now we are almost there because we have this surface. So what is the total number, the mean number of, sorry, there is something I haven't done. I have to take the expectation of this over all realization, because you start from here, you have one realization, you start from there, you have another one, and then you average over all of these sausages so that it becomes a deterministic number, right? Otherwise, you have something stochastic, you have a piece of a tube which is stochastic, and then you average over, you take the measure, and now you average over all of this, and this is the result. Okay? This is classical tools in classical probability theory. People are looking at a lot of calculating this, and I'll mention something in a second about this. So what is finally the mean number of the expectation of the number of bound molecules? So this is a random number. Each time you do this, you have a certain number, and you average over realization. So this is this pi tau log of 1 over epsilon multiplied by the probability of activated multiplied by the density, because this is the surface multiplied by density is a number, and this is the effective PAC. This is the probability to activate a molecules after when this is called the rhodopsin, after the rhodopsin molecule, or it's any kind of molecule, the rhodopsin molecules hits it. And this, of course, we have also to average over the time, because if the time here is the random time Poissonian time, you have to average over your mean Poisson process, and you get tau mean. Okay, so what is wrong with this model? Yeah.
How come the size of the Wiener sausage does not depend on the diffusion coefficient?
The size of the Wiener sausage
Does not depend on D.
It should. It should, no? Let me think. If the diffusion constant, yeah, because this is probably assuming that D equals 1. You're correct. There is a diffusion coefficient here somewhere for the pass. So the correct units should be d tau, right?
But the ball is just a surface, right? Yeah.
The what? I'm sorry?
Just a surface, yeah, okay. Then.
This is the surface. This is the surface. So this is, yeah, d tau, correct. So what is wrong with this model now that we've corrected this basic thing? What is wrong? I mean, it's not wrong. We are counting things twice. Because of what? Why are we counting things several times, although it's not in the figure? What is the property of the Brownian motion? If you have a Brownian motion and you simulate it, or what do you observe? Is the Brownian motion doing this? No. It does what? It comes back again and again and again and again. Okay, so now this is something that we haven't taken into account, because we're saying that each time the particle encounter, it activates. But if you come back to the same place, it's already activated, right? And so the real calculation, a calculation that would account much more for reality would mean that I have to discount all of the part of the Wiener process where you have the loops. We should, if we want to be efficient, discount all of this and reduce some calculation. But this is quite, this is, for example, mathematically quite difficult to look at what is the distribution of point at where the trajectory comes a multiple number of times given a certain time interval. I'm not going to do it. But this is to explain to you how you do some calculation. This is an example of a process of amplification that occurs everywhere in nature. This is the basis of amplification. That's why I wanted to do this. It has some biological meanings, and it is found almost everywhere. This is how you amplify on the surface of a cell by diffusion only for a certain time. All right? Okay. Now we'll change subject. We'll go back to the Ecole calculus. So I said, you want a break? It's all right. It's a good moment to give you, let's say, 7 minutes break, 10 minutes break, so that we'll do a break and then we'll resume with Ecole calculus. I'll do Ecole, and then I'll show you how we go to partial differential equation, which I think is important. Again, this is textbook, but it's not necessarily what are the typical presentation of this. All right, so we will do this, the PDEs, the Fokker-Planck, so that those of you who are not familiar with the stochastic processes, you know, now it's clear. And then we will start the analysis of the equation. I mean, right now we show the equation, and then we will see how to analyze them. Okay, break. Physics with a lot of variables, a lot of freedom. So it's not the classical physics that you think about the Newton or a solid. It's particle physics where you have millions of particles that you have to do averaging, that you have to look at what happened of the geometry. So this is a new way of thinking, not classical. I mean, classical in the sense that it's classical physics, but you have to have new ways to understand with the classical tools this new type of physics. If you're interested, there is a Physics Today paper that in the last month, that we wrote about these ideas. It's 1 page or 2 pages explaining that ultimately the new biology, the new mathematical physics in the biology uses the classical physics. But now you have to deal with many degrees of freedom. And this problem of change, how you change scale. Nobody knows how you change scale. How you connect a bath of continuous particle with discrete event. How do you do this connection rationally? How do you analyze it? What is the meaning of electricity? Those are basic questions. They are not answered. And I'm not talking about sophisticated questions. This is the basic comprehension of what is electricity in cells. It's not clear. I mean, to us, which means we don't know. Okay? All right. So this is not part of mathematics. This is what I have shown you now. This is part of what is called modeling. Modeling means how you go from a problem to some equations. The math starts when you do analysis, when you extract information, when you extract solution from equation, or you simulate. This is called modeling, all right? Now I'll go back to math, to look at wait, let me find where I am. To discuss, for those who have never seen this, I think it's important. I've been much too far. Wait. So we have discussed these applications. So we haven't started the Ecole calculus, right? Okay. So now we'll stop all of this and let's discuss. For those of you who have never seen that, I think it's very important to discuss what is the Ecole calculus, because it will allow us to define different types of stochastic integrals that we haven't much discussed so far. And it will allow us to derive what is called the Fokker-Planck equation and the mean first passage time equation, from which we can do all the calculus. Okay, so the essence of this is the following example. So if you have, again, x1 and x2, this is two deterministic functions. You know, by definition, if they are regular, the regularity is good enough, that dx1, x2 is x1 dx2 plus x2 dx1. But this is not correct if x1 and x2 are two stochastic processes. So I'll give an example that we'll do together, and we will start from there. This is b delta t plus a1 dw, and I'll take dx2, which is b2 delta t plus a2 d omega, and this is the same omega here and here. And those are constant, a1, a2, b1, b2. All right, so I want to take this to calculate this quantity, x1, x2, and this quantity, and I would like to compare to see where the difference comes from. Okay? So let's do the calculation. We can integrate this, right? So what it gives the following. x1 is just b1t, because those are constant, b1t plus a1w plus alpha 1. You see, this is x1 of t, x2 of t, which is b2t. So again, you do it for yourself, and you make sure that I'm doing things correctly. a2 omega plus alpha 2. Now I can calculate x1, x2, and differentiate. All right, so let's do this. x1, x2 is the product. So this is alpha 1, alpha 2. Now we have to calculate. So the term in omega is a1 alpha 2 plus a2 alpha 1. Now the term in t, or in omega squared. In omega squared, you get what? In omega squared, I think we have only one, correct. a1, a2 omega squared plus the term in t omega that comes from here. So this is b1 a2 plus a1 b2, and this is t omega. And then there is a term in t squared, which is b1 b2 t squared. So we need 9. We're missing which one? Omega, t omega. T is missing, right? Yes, that's good. So this is b1 alpha 2 plus alpha 1 b2. That's it. And now let's differentiate this d of x1, x2. Right? You're saying that I'm completely stupid, you know, I just integrate and I have to differentiate. But it's okay, because I want to calculate the difference. Okay, the differentiation of a constant, this is a constant. The differentiation of d omega, this is a1 alpha 2 plus a2 alpha 1 d omega. Then this is plus a1 a2 d omega squared. This I don't know what it is, so I leave it this way. I don't touch. This is, again, I don't know what it is, b a2 plus a1 b2 t of d omega. This I know because b1 and b2 are constant, and this is just 2b1 b2 t. You differentiate this, and this is also known because this is b alpha 2 plus alpha 1 b2 dt. All right? I haven't made anything yet. I just wrote this d, and now we have to understand what is the meaning of this d. Okay, so to calculate, to understand the meaning of this, I would like to go back to what we discussed. So how are we going to calculate d of omega, d omega? And for this, we need to look at this more carefully. again, this is now some mathematical treatment that we have to understand. What is d of omega squared? And for this, I'll propose to compare this. Basically, we would like to compare this with omega d omega, right? And so to calculate this, we can also compare the integral of the function. So I can integrate this or integrate this to compare them. So I'm interested now in calculating integral from 0 to, let's say, capital T of omega of s d omega of s. And for this, so to calculate this, to compute this quantity, let's call it T, no, well, let's call it S of T. To compute S of T, we will start as we did last time. We will introduce the sum Tn, which are the sum from 1 to n of the like Riemann sum, if you want, of this quantity. So now we decompose 0t, the time interval from 0 to t, into segments of the same delta t. So we go from, let's say, t0 to tn. So we sum from 1 to n, and so we have omega of tk, omega of tk plus 1 minus omega of tk. Now, what can you say about this? So this would represent the discretization of this. D omega, this is the discretization in this interval. And this, I choose omega tk, which means I choose to calculate. So suppose you have a function. So you discretized it. So this is your time interval. This is now Brownian motion. Take the difference between these 2 points. And this is tk. This is tk plus 1. I choose here omega tk. Now this is a choice. You can approximate a function, and it doesn't matter in Riemann or any kind of integrals, the fact that you choose here tk or anything in between. But for the stochastic processes, it does. And this is very important because this is a source of many confusion in stochastic processes. It's very important to understand that you have the choice. And now the question is, what is a physical choice? Are all the choices physical? So the answer is no. Here there is a choice, and it's very important. So if you choose here this is called Ito calculus. You could choose here omega tk plus 1. Right? This is if it was a purely deterministic function. And if this is a Riemann sum, if you take k goes to infinity, it converges to the classical integral. Here, it's not going to be the case. And this is the choice 1. And this choice, if you take this instead of this is called the Stratanovich calculus, Stratanovich form. The paper. This is called the Stratanovich form. And you can also have any, you can, if you think about any convex combination, it's S omega tk plus 1 minus S omega tk plus 1. So for example, for S equal 1/2, you have also a form which is which actually gives the classical integral. Now, which one is the correct one? What? Stratanovich? Why?
It's not anticipating?
The one it is not anticipating is this one.
Yeah, yeah.
So this is exactly the response. This is because it's not anticipating, it doesn't see the future. But sometimes in signal processing, you see this form. Why? Because if you have a radio signal that you have acquired and you process it, you know the future. And it can come out that you end up with a Stratanovich form to calculate things. Because you know the future. Okay? So people did not abandon all of this, but I want to mention that to you. This is in books. This is discussed in length in books and in papers. And it's even not clear in papers why people are applying Stratanovich form to physics problem. But it is done. Now you have to understand what's the origin of this. Okay, so now we are left here. Now let's do the calculation with this, and at home I'll leave you this to do. Now let's start the calculation. Can we calculate Tn, which is, so you have your Brownian motion multiplied by this quantity. Can we rearrange this? The answer is yes. We are going to do that now. Tn can also be written as a difference of squares. So this is omega, let's write it, omega k plus 1, tk plus, okay, let me not define omega k as omega of tk, right? So I'm not going to repeat all of this. So omega k plus 1 squared minus omega k squared. So if I do this, I am left with 1 minus omega k squared divided by 2, so that it is minus 1. We are left with omega k plus 1. And we have introduced this term, so we have to remove this term. So this is omega k plus 1. Somebody has to check, right, that I'm not doing a crazy thing. Omega k squared divided by 2. Now, omega k plus 1. Is that correct? This cancel with this one. This plus this equal minus omega k, which is this one, and this is just this one. That's it. Okay? So this is the sum. So if you sum this is a telescopic sum, everything will cancel out. So it should be omega squared t divided by 2 minus omega of 0 divided by 2. And this we are left with omega minus, so this is minus all of this. So this should be 1/2 omega k plus 1 minus omega k squared. From k equals whatever, from 0 to n minus 1, something like this. Or to n, Tn. Okay, are we good? Is it correct? Yes, this is correct. So when n goes to infinity, what is the, so let's assume for simplicity, this we can always assume, because this is defined up to a constant, that this is constant is 0, I don't care. Now, what is the limit of omega squared t when n goes to infinity? Where is n here? Do we see an n? There's no n. So the limit is this. Okay, so this we know. So we have a sum of Brownian motion, and we're trying to study a limit of sum of Brownian motion. The question is, what are we talking about here? Where is the limit, where it goes? Now here comes an interesting question. So this is n goes to infinity, so we refine the steps n going to infinity, and we have found that in the limit in the space of non-anticipating function, as you mentioned, Tn, as n goes to infinity, is going to, the limit is this integral. So if we can calculate this, we will know how to calculate this. So we have this now, this expression, and now we would like to look at the limit when n goes to infinity. So we are left with this term. What is the limit of this difference? We have now a sum of Gaussian. What is the limit when n goes to infinity of this? I mean, the first question is, does this have a limit? You see, you are summing an infinite number of Brownian motion squared. So who knows? This is called the, what is, okay, when you have a sum of random, of identically distributed variable, you have A, they are identically distributed, and you look at the sum. Let's go to the basic things. So those are Brownian motion. I mean, those are stochastic variables. They are random variables. Suppose all of them are independent, identically distributed. Does this, is this sum, if it converges, where it should converge? To which number? To which, oops. Yeah, I cannot move this one.
Isn't it equal to the square root of n times the Gaussian variable?
Yes. Okay.
If the mean is 0.
If the mean is 0, but if the mean is not 0?
The mean times the number of variables plus correction, the other square root of n.
Okay, so then the thing we should anticipate for here is to first try to calculate the mean of this quantity. Is it finite? And if it is finite, to look at if this number, although they are random numbers, when n goes to infinity, possibly they will select the mean value, and this will be the limit. Okay, so let's look at this question. What is the mean of this variable? Is it finite, and what it is? And then we will proceed. So why is it important to manipulate correctly Brownian motion and all of this? Because if you do some simulations, or if you want to analyze things with noise, correlated noise, of all kind of noise, you have to usually look at this quantity, how they are transformed into transformations. And you should not be afraid of doing the calculations. This is why I do all the calculation on the board. It's not that I could say, okay, you do your calculation at home. You should see all of this so that you should not be afraid yourself of repeating all of this. Okay, what we were discussing is the expectation of Tn. So who can tell me what is the expectation of Tn? All right, so let's just replace. This is 1/2 of the sum of the expectation of omega k plus 1 minus omega k squared. So this is what we have studied at least 3 or 4 times. This is simply the this is a Brownian variable of increment delta t. This is exactly what we said. Tk plus 1 minus tk is delta t. So this is, okay, let me write it this way. This is tk plus 1 minus tk. Let's assume this is of d. The diffusion coefficient here is 1. I mean, I don't, so that maybe 1/2. Yeah, what is necessary to have this? Right, I didn't tell you that this omega k here is characterized by a variance. I assume it is 1, so that... all right, so now we have to sum this from 1 to n with 1/2. And this is equal to what? Simply t divided by 2 now. All right. Now suppose let's accept this result for a second. Suppose I'm proving it. I will show that then what we need to prove is we need to show the convergence of this towards the mean. And we will show this the convergence in probability. But let's suppose we have this for a second. Then, what do we have? We have the Tn. So suppose we have the proof. Tn would converge to omega squared t divided by 2 minus 1/2 of t. And now, which means S of t, because this is a convergence, and this is, by definition, this is a limit. So we have integral from 0 to t of omega of s d omega s equals omega squared t divided by 2 minus t divided by 2. Right, this is a result in limits. This is whatever it is, and this is the limit of what we have seen, of the Tn, which is this. Now you can differentiate, or you can write this with the infinitesimal version. So integration of 0 to t dt of this so we can rewrite this as omega t d omega t equals d of omega t that we didn't know what. So let me multiply everything by 2. Just multiply by 2 minus dt. So I'll take the dt, I'll put it there. So this is plus dt. And now this is exactly what we didn't know, what to calculate here. You remember we said this, and now this is not the classical term, which is 2 omega d omega. This is 2 omega d omega plus dt. Okay? And so this, you'll start to see the difference between the classical calculus and the new Ito calculus. This is where it comes about and how it propagates. Because now, so you can have this, will give us, so 2 omega d omega minus, no, plus dt. So here, actually, what you can prove, I'm not going to show it. This is t d omega plus omega dt. We can show it the same way that I have shown this. You have to calculate you redo everything, and instead of calculating omega d omega, you take t this, and you can redo all of what I have done, and you'll be able to show this. So ultimately, what is missing here when I have these stochastic processes? The only difference, this is not going to change if you multiply x1 dx2 or plus x2 dx1. This is going to be the same. This is the same because this is the same calculus. So the only difference is going to be here, delta t. So what is the difference? We can write it this way, dx2 dx1 plus x1 dx2. So d of x1 x2 equals this plus a1 a2 delta t. Okay? This is for omega, a Brownian a process of variance 1. Okay, so now we have assumed this. Now let's prove it. All right, so now we have this quantity. We assume that if this is correct, we plug that into this. So now we have to prove that what? We have to prove that Tn converges to, so what you said was the large number theorem where this mean is 0, but now when it's not 0, we have to, it's much more simple. So let's prove that Tn converges to the expectation. And how do you show that? We want to look at the difference, Tn, minus the expectation. And we are going to prove, you are going to use what is called the classical theorem. This is maybe the only time where I will use something of classical theorem. You have to use the Chebyshev inequality, which give you an estimation when you have a random variable minus the expectation. This is larger than epsilon. This can be estimated by the variance, which is the expectation. This is less of Sn. So why I wrote here S1? Okay, this is Sn. Sorry, this is Tn. Okay, let me write it this way. This is Tn squared divided by epsilon squared. So it goes like this. So this is called the Chebyshev inequality. This is classical. Not going to prove it. So it says that for any epsilon positive, if you have a random variable x, the probability that x minus the mean of x, this is larger than epsilon, this is less or equal to the variance sigma squared. So sigma squared means expectation of x minus the mean squared divided by epsilon squared, which is finite. I assume that you know, we assume that we have finite variance. And so this proves that if we can show that this goes to 0 when n goes to infinity, if we can demonstrate this, this will show that we'll have in probability that almost everywhere the limit of Tn is the mean. And this is what we wanted to prove. All right. So what is now, we have to calculate what is the this Tn minus the mean, so the expectation of this. All right, this is what we are left with. So let's prove that this goes to 0 as n goes to infinity. All right, so sigma n, let's call this sigma n squared. Sigma n squared is the expectation of Tn. So this can be also written expectation of Tn squared minus expectation of Tn everything squared, right? Because you have the squared here. So this is, I put it square, so Tn squared minus the product twice Tn multiplied by this, and you take the expectation of this, plus expectation of Tn squared, so you are left with this one, right? You double check everything. So all right, this is what we get, and now we need to do this calculation. So this is the sum of what? This is the expectation of the sum. What is this Tn squared? Yeah, this is correct. So this is d omega k squared minus the expectation of Tn, which is the sum of d omega k, this yeah, with a squared here, everything squared. I just introduce in here what is the definition of Tn. Okay, and so now what do we have here? Okay, so this squared, I can also develop it. So this is the sum. The first one is a sum from 1 to n of k and q of what? Of d omega k squared d omega q k squared. And now we have the expectation of this. Is this correct? Yes. I just take it squared, put it twice, and use as we have already done before. And this term, this is minus the sum of, again, the same quantity. This is the expectation of the same, but except now we have the expectation of d omega q squared, expectation of d, sorry, it's omega k squared, and again k and q. And this, so for example, what happened when k equals q? Now, what happened when k is not equal to q? Those are independent, so this should cancel out. So we are just left with what happened for k equals q. And we can always then get, because this is a minus, this is always less than the sum for k equals q of this squared, which is expectation of d omega k or q, it's an important, power 4. From q equals 1 to n, or n minus 1 or n plus 1, I forgot. So now we are left with this sum to calculate. And now for this we are going to use the expression of the Brownian motion, and that will be the end of this calculation. So now what is this sum? So first of all, this sum is the same because we have n independent Brownian variable. So if they are all independent, this sum can be seen as n time the expectation, let's say, of the first one. It's unimportant, of d omega 1 to power 4. So now what is the expectation of d omega 1 to power 4? And then there is an n that we are not going to, we should not forget about this one. So what is this? So this is the probability distribution. This is the expectation of this variable. So we need to have the probability distribution function during time step delta t, and we have to integrate x to the power 4 p of x. We have to integrate, let's say, from minus infinity to plus infinity. This is by definition the expectation of this variable. Is that correct? Yeah, something like this. Right? We are in dimension 1. So we said that, you know, all the increments here are all independent. That's why I used the first one, delta t. So this is the transition probability. This is transition probability for a Brownian variable during time delta t. Condition that at t equal 0, it was in 0. This is what we said, omega of 0 is 0. So then this is what? This is, in dimension 1, this is 1 divided by 4 pi delta t. So we said diffusion coefficient equals 1, square root exponential of x squared divided by 4 delta t. and then we have to integrate dx, x to the power 4, and this is twice, because it's symmetric, from 0 to infinity. Now this is what we need to calculate. Actually, we don't need to do the calculation. Yeah, and what is delta t? So delta t corresponds, n times delta t is the entire interval, which is capital T. So delta t is t divided by n. And so we are interested in the limit when n goes to infinity, right? So what we just need is to see the dependency in delta t, which will give us the dependency in capital T. Yeah, I'm sorry, I haven't... are you with me? Yeah, okay. Not hard. It's elementary calculation once we have cut it into small pieces. Okay, so now how do you do this? This is just changing variables. U equals x divided by square root delta t. And what do we get from this? We get twice. So x to the power 4. So first of all, in the exponential, you get x. So this is u squared divided by 4. Dx is equal to square root delta t du. So you get square root delta t here, du. You have x4. This is square root delta t to the power 4, u4. And then we have to divide by how much? By 4 pi delta t. Right? Integration from 0 to infinity. And so we need to look at the delta t term. So this goes away, this goes away. This integral converges, and I don't care, I don't need to calculate it. And we have here delta t to the power 2, because we have square root and 4. Multiplied by a constant. I don't know what it is, and I don't care. And this is, so then, let me remind you that there was multiplied by n here, so I have to add the n, n. So n times delta t is how much? It's t divided by n squared multiplied by constant, which is ultimately t squared constant divided by n. And this goes to 0 as n goes to infinity. All right? And I think we are done. This goes to 0. This goes to 0. This is the inequality. So this is okay, and this goes to 0 as n goes to infinity, which shows that in probability we have this convergence. Okay? So now this is the understanding of what we are manipulating. When you manipulate the stochastic integrals, you manipulate the limit of Brownian variables. Each time you see this, you cannot decompose into a sum. This is what you have to do. You decompose into a sum, and then you analyze the sum. I'm giving you the conclusion about the way of thinking. Okay, so this is important because now you see when you have to calculate, and this is the next thing we are going to do. If you need to calculate a function of a Brownian motion, we'll have to pay attention to the fact that the derivative, for example, what is the derivative of a function that depends on x? So suppose you are looking at the f is the mean first passage time. It gives us the, then if you need to calculate quantities, we have to pay attention because of this propagation of the Ito calculus. Okay? Okay, let's do 10 more minutes and then you are free. Again, this is textbook, I'm sure, but if you haven't seen, or if you have seen version where you manipulate Grunwald inequality from a mathematical point of view, I'm not sure you get the spirit of where we are going. You understand how to manipulate things, but it's important to understand the where we are going with all of this, and where the terms are coming, why we do this approximation, when things are coming from the physics, when it comes from the mathematics, when it comes from the stochastic processes, to divide in your head, you know, where things are coming from, so that when you find a new problem and you model it, you have the tools to react. Okay, so this is done. This is finished. And now we can go to the hard stuff. So you can do at home. You can look at what the Stratanovich form gives. That is, if you have the Stratanovich, how this is going to be changed? Plus is going to become, that's right. Plus becomes minus, and if you are exactly at the in between, let's say you take the point in the Riemann, which is the average of the top of the, I mean at a point, the beginning minus the final point. What do we get instead of minus? So if this is minus when we took, yeah, it takes 0, that's it. So this you have to show it for yourself. Yeah, and this is also important. This is the basis of, you know, when you do signal processing, when you do tracking of signal. Tracking of a signal is a problem backward in time. Because if you have a signal, for example, you know, you can go backward, so you have information about the future, but you want to use your information and all your signal processes, for example, to extract features in the signal. Of course, it's different if you have a radio and you have to denoise the radio at the same time the signal is coming, and then you have to, you know, how you do this denoising at a real time. And this, yeah, so there's all kind of algorithm, but I mean, I'm not going to present that this year. Okay, so now let's go to the next stage, which is called the full. I mean, there is other. Okay, I'll skip some exercises. Now let's go to the full Ito formula, which is the following. So Ito's formula. So if you have a stochastic process, you would like to calculate information about the stochastic processes, like what is the mean, what is any moment of interest, conditional information, what is the probability to find the particle outside, knowing that it has hit something. So in principle, you would like to calculate, can we calculate for any function f you want, f of x of t? Basically, when f equals squared, I mean, I'm interested in this differential. We found it when f equal to squared. That is, f of x equal x squared. This is just what we did here. So now what is d of f of x for a general function f? Let's suppose f is sufficiently differentiable, at least 3 times, maybe less, I don't care, in a domain. Can we calculate this quantity and what it gives? So if you have a regular function, what do you get? What you get is d of x. If you have a stochastic process, which is, let's say, x dot equal b of x. So you have along a dynamical system, so you have to differentiate with respect to your field. This is df dxi at position xt, right, multiplied by dxi, which is here bi of x of t delta t. So this is the from, let's say, if you are in dimension n, so omega is a, let's say, any kind of domain in n dimension, dimension 2, 3, 4, whatever. So that's it. This is the linear. This d of f. This is called the linear, linearized form, and that's it. And the rest you have term of dt squared, which I don't care. What do you get now for Ito calculus? What do you get for a stochastic process? Instead of having x dot equal this, now I'm interested in x dot equals b of x plus sigma of x w dot. So how do you calculate this when you have a Brownian process? A Brownian plus, a stochastic process. Okay. So we've done more or less everything. I will patch the important part. And this is called, the result here is called the Ito formula. And this is important because from the Ito formula, you can calculate, we will derive the mean first passage time equation, and the Fokker-Planck equation, and all of these important equations that then we can solve. So to do this, we'll do the same as before. You want to calculate f of x of t minus f of x of 0. So you have a stochastic process, and basically we decompose in time along the trajectory. So this is 0, this is x of time t. It has a deterministic element and stochastic element, and this will decompose by cutting into interval of size delta t. This is tk or t I, and this is ti plus 1, and this is f of x of time ta plus 1 minus f of x of time ta. So we look at, this is a decomposition into small increments. The difference between this and this is the sum of these increments. And now what we do is, let's look at dx. I'll write it this way. It's an important dx of dx, this is b of x delta t. So if we are looking at point, let's say ti, let's write it x of dx of I. This is by definition xi plus 1 minus xi, where xi is x of ti. So this is this difference. This is b of x at xi plus, so you can, there is a matrix here, this is called the tensor, sigma of x at position ti, and now this is d omega I. So it's a little bit more complicated than this. Okay, so if we have in n dimension, B is a vector field. So this is B1 Bn. Sigma is a matrix, and omega is also a matrix. So omega here, this is n dimensional Brownian motion. This is the notation. Let's say we're in dimension n. Sigma is a matrix, so I'll call it sigma k q, that can depend on x. So this is called the diffusion tensor. All right, so this in principle is the product of a matrix multiplied by a vector. Okay, and then so what we are going to do now is just use a Taylor expansion of this difference to order 2. Right, you have a function of b minus a. This can be written as a function. This is, so using the Taylor expansion, the first order term will give us df dxk at position xi multiply by dxi, which can be replaced by this. And so this is b of xi delta t plus sigma. Now we have to be careful. So this is now d omega I. So now in terms of matrix, this is the coordinate k. So this is k, and then I multiply by q, and here I use the q term. Or I can write it, okay, I will write it this way. I will write it sigma. You see, this is, I take the coordinate, k coordinate here, and this is the coordinate k of this. Plus, so this is for dimension going from 1 to n, plus 1/2 of the sum of ddf dxk dxq of this k and q. So this is the same, bk of xi delta t plus sigma at position xi, sigma of position xi d omega I. So this is k, this is the k term, multiplied by the term which is the term q, qxi delta t plus sigma x. This is the part of the class which is the most boring. It will become much more interesting when it will be applied. But I have to go through all of this. If you don't do it, you will be always afraid of writing it yourself. So let's do all the, calculate. This math is about calculation. So sigma x I d omega I, and this is the matrix, the q component of this matrix, right? Which means we have to sum. This is later on the sum of all this vector multiplied by this matrix. Okay, and then plus something that is negligible. Plus delta t squared. I mean delta t, capital O of delta t. A little capital O of delta t squared. All right, so now what do we do with all of this? What is the term? So this is a stochastic equation. This is a stochastic equation. And so like this term, there is a term that is going to be dependent on delta t, and a term that is going to be dependent of the noise. Time, noise. So here we have to identify the same, to group what is depending on time and to group what is depending on the noise. So let's do this. Where is time here? The first term in time is in here. And where else? So where is the noise term? There is a noise in here. There's a time in here. And now we need to analyze this term, which is, let's suppose this is just dimension 1. Then we have here delta t multiplied by delta t. So this is delta t squared. Delta t squared go to the garbage. We don't care. Delta t multiplied by dq. This is exactly, you remember, this is exactly the calculation I have done here. Except this was dimension 1. This is t multiplied by noise. And t multiplied by noise, it's really like this. And so basically to order delta t, this is for delta t small. I mean, this is an integrated version. But here this is delta t multiplied by d omega. So we'll get delta t multiplied by d omega, and we will see that this will go to 0. I mean, this is not going to contribute because of the Brownian motion. The expectation of this is 0. Okay, so now let's rewrite this in terms of time and noise. So this is a sum for I going from 1 to, let's say, capital N. And N will go to infinity. N here, little n, is the dimension of the space. So now this equal to this, and this here equals, so what is missing in here, this is a different, I've used Taylor expansion at each point. So now if I want to have this equal term, I have forgotten to use the sum from I going from 1 to n. Okay. So now, what is the limit when n goes to infinity of just this term here? Remember, so we cut and we have applied the Taylor expansion. And now we are going to study each term separately. So what is the limit of this term? Yes, that's right. So I need to move on to the next board. Yes, that's right. This is exactly the integral of what?
Radian of f.
Yeah. So this this is finite, so I can just take the sum here. This is exactly the Riemann sum for this. So this term, now you have to write everything. I don't, because I'm on the board, so I just do big arrows. And this term converges as n goes to infinity to the integral from 0 to what? To t of df of dxk x, this is xi, so this is exactly your sampling. So this converges now to the continuous path x of s, b k x of s ds. Now this term here, this multiplied by this is exactly non-anticipating function multiplied by this. You go to the limit. This is exactly the definition of the stochastic integral. We'll get plus integration from 0 to t. So everything here has to be thought, you have to think about it as a limit. So you just take what we have been doing. This is, so I forgot this first sum. There is a first sum from k to little n, which is a dimension. And now there is another sum, which is the same, k from 1 to n. So this you have to repeat at home for yourself. ddf dxk x of s multiply by, so if we do it with the full notation, so this is a matrix sigma k q. This is a matrix, as we said. At position, I write it once, everything, and then you'll do it. D, and then we have to multiply by d omega of q. And here you have a sum. The sum for q from 1 to n. Right, because this is the matrix here. So I told you that this can be seen as a matrix sigma ij, and that you apply to this vector. So I just multiply everything. So it depends on k, on q, and this is the entire sum. All right? Now, as I said, there is a term that you will have to do it at home. But then there is be one term here that is going to be very important for us, because we know that what is the limit when we are going to get the product of d omega multiplied by d omega here. This, we have done it. We did it here. So let me rewrite this. We get, there is one more term that I'm going to rewrite, which is 1/2 of the sum from 1 to capital N of the sum of ddf dxi dxq dx k dxq. And then we have to be careful. So this term here, so this is a plus b multiplied by a plus b. So I take b multiplied by b. The rest I say I don't care because it will go to 0 when n goes to infinity. This is sigma, so this is k. So this is sigma k q multiplied by d omega I, and this is going to be, let's write it this way, d omega I q. And the same here, this is going to be sigma. So now this time we have, no, this q is not good, so let's call it q1. And this we have the q, so this is q, q2, d omega I. I mean, it's true that there is also, okay, I'll write it this way. And this multiplied by q2. And here we have to add. So there is a sum here on k, on q. And here I have added a term, which is the sum here on q1. And here a sum on q2, which I'll remove all the sum and put it there. The sum of q1 and comma q2. So I have 5 sums, but I don't care. What is the limit now of all of this? Don't care about the sum. When n goes to n goes to infinity, so this is the sum of the I. What is the limit of this? This is what we have done, what we just did, no?
The regular integral of what is inside?
Yeah, it converges to what? So this is a sum of an infinite sum of Brownian variable. They are going to converge to the
mean.
That's right. What is the mean of this? You have to take the mean. That's right. So expectation of this, you have 2 Brownian variables. They are going to, everything will be cancelled except when they are all equals. That's right. And then when they are equals, it means that q1 equal q2. So this is sigma k q1, sigma k q1, d omega, this is going to be delta t. And then we are left with everything else. Nothing else has changed, which is going to be the sum for k, for q and q1. We don't care about q2 because one sum drops. ddf dxk dxq, this. And now what is the infinity? I mean, I forgot something, which is the integral. Let me write it properly. This is the integral from 0 to t, capital T. This is ddf. I'm writing everything so that it becomes clear. dxk dxq. So sigma k1, sigma k k1, y2k here. Now this is incorrect. This is q here. This is q. So this is k, and then we are left. So this is x of s at position s. This is x at position s. This is x at position s, and ds. And there was a factor 1/2. Are we good? I think so, no? And then we have to sum here over k, over q, and over k1. And actually over k1, you can have this over k1 here, like this, over k1. And this is simply actually the matrix sigma sigma transpose, which is here. If you do sigma sigma transpose, this is exactly this matrix. That's why in probability, in the Ito equations, you get always this sigma sigma transpose that comes. And this is the equation. So what is the summary of all of this? Now we need to, this was for the case of the deterministic function. And now for the case, you can now differentiate everything with respect to capital T. So you don't have to write anything. Just write here d of f equals this plus this plus 1/2 of this, right? Because we have calculated here this quantity f of capital xt minus f of x0 equals this term plus this term plus this one. And this was the intermediate term. Right? 3 terms. And this is what in the PDEs will lead to the Laplacian and what you have seen when you study the diffusion equation, where it comes from. It comes from this formula, from the fact that here you have the second derivative. Okay, you have to redo it for yourself, for those who have never seen that. I wanted to do that for those of you who are not mathematicians, because this is how it is done. By understanding that this is a limit. You see this is a limit. And you replace basically, because we know that at the limit this is equal to the mean, so you replace by the mean. All right, so this is the df. This is the part that contributes to the other one, the time. It becomes linear with time, and this is becoming the stochastic term. All right, so I'll stop here. Next week, I would like to show how you use all of this to calculate mean first to write the equation for the mean first passage time, to write the Fokker-Planck equation, and then we'll be ready for some nice application that I have used, for example, to extract information from super resolution data. How you use this notion of expectation and conditional expectation to calculate how to extract mean, the drift and variance from data, from trajectory that you can acquire from your experimental data. All right, and then we'll do some conditioning so that you can see how you can calculate thin condition in the future. And then we'll be ready to go directly to the, I will skip some exercises and application, and we'll go for the exit problem. All right, see you next week.